Well, hi, my name's Sue. I'm a biologist, and I will be your final act for the symposium. So when I was young, I thought it was really funny how no matter how smart we call ourselves, nature has a way of always outsmarting us, whether it's earthquakes that shake our building or viruses that evade our smartest vaccines. So that kind of has shaped my career path into asking and looking into nature to help us fix society's problems in energy and pollution. So when I say energy, these are the three most common forms of energy in your daily life. But today we'll focus on heat, things that produce heat, one of which is natural gas. So when you step into your kitchen, it's like 12 a.m. midnight, and you're trying to cook ramen, and you turn on your gas, it makes that t-t-t sound. That's natural gas providing heat. It causes the flame. Also, natural gas is found in your farts, and hence why some people try to produce their own farts. I don't know if that's a good idea. But mostly, natural gas is found in nature, under the ground. So this is a picture of Canada during winter, a lake in Canada, and there's so much natural gas coming out from the ground, underground, into the lake that it freezes. The bubbles freezes during winter. So if we focus on natural gas more, it is made mostly of one type of gas called methane, which is going to be the main star for tonight or today. So methane is flammable, hence why we see fire in the previous pictures. And it is the main source of our heat and electricity in our homes. So just for size comparison, here's our, favorite water molecule, that H2O, and methane, just so that the size is comparable in your mind. Methane is really great for energy, so how do we get it? So we have a process called shale gas fracking. That's how we get stuff for our gasoline. Essentially, we build these giant machines that drive a bullet into the ground, bam! And then we get our stuff for our gasoline. But at the same time, since we made a giant hole in the earth, we get these natural gases coming out along with it. And there's so much natural gas and methane coming out, we can't store all of it because it's too expensive to store and transport gas around the world. And instead, we just let it out into the environment. And here's a map of all the sites in the world that has shale gas fracking along with methane emissions, which is problematic. Why is this problematic? Because methane is a potent greenhouse gas that contributes to global warming more so than carbon dioxide. Also, didn't I say we could use methane for energy? Well, since I just told you we're just burning it into the air, that's billions of dollars we're losing annually. So in a perfect world, what could we do? Well, it would be really nice if we can collect our methane, put it in a technological magic hat, sprinkle some magic in there, and out comes out gasoline for our cars and energy for our homes. But currently, there is no technology that cheaply can do this process. So people like me, we're really interested in going out into nature and finding a solution for this problem. And actually, a solution already exists in the form of bacteria. This bacteria is called Methanotrophs. They're found all over the world in deep water, oceans, and even salty lakes. And what they do is they break methane. What do I mean by that? Just like how we eat pizza and we grow sideways, these bacteria eat methane, break it into pieces, and use that to grow spirally. And so people are like me, we're oh my God, how do you do that? And so that's my research is understanding how they do that. And what they use is a protein in the bacteria to break the methane. And when I say protein, you're like, oh, what? It's maybe keratin in my hair or the collagen in my face that makes me wrinkle-free, hopefully. But there are proteins that actually do more. They can actually break things. And in the case of this bacteria that I showed you, they have a protein called pMMO. And that is responsible for breaking methane. And I'm really interested in understanding how does pMMO do this magic. And this is kind of like an analogy to me always wondering, oh my God, alarm clock, you never fail to wake me up every morning. How are you always on? And that's because if I open it, you find out, oh, it's the battery driving the energy towards my alarm clock. And then I look at it, I'm like, oh, I know there's a plus and a minus, but I'm not an electrical engineer. How does this work, right? And I'm really curious. And that's the same fascination I have of understanding how pMMO, this protein, can drive the bacteria to grow and break methane. So what do we know so far? Here is a giant pMMO and methane next to it. So what we found out is it needs copper to break the methane. And when I say copper, you're like, open your wallets and you see a penny, right? That's where copper is found. So here's an ironic statement. Drop in a penny and save billions of dollars, right? If we can figure this out. Unfortunately, it's been difficult. Here's the limitations of why we haven't solved this magic process yet. Because when I wake up and this alarm clock's ringing, so I take it and I break it into pieces, and now I'm like, oh, here's a kind of half-broken battery. Let's study it. It doesn't really work that way, right? What you're doing in that process is you're ripping it out of the wires, out of the contexts it's in. And in reality, what we would prefer to do is put the battery back into the wires, see how it's connected, and see what other components it's interacting with. And that's the same process with how we study my protein. We have to break the cells, extract the protein that is unhappy, right? And really, what can we learn from it? So there must be an alternative approach to studying this really great protein. And that is where I fit in, is now instead of breaking it and just picking up the pieces, right, I'm going to study the protein while it's still in the cell and still functioning and very happy. And how do we do that? So instead of breaking it, I decide to just take the bacteria, use technology and genetics to just change the DNA. And by doing that, I tell the bacteria, hey, let's make different pMMOs, different proteins with little bits of nips and tucks. Like, I'm going to remove my thumb. How do I now react, right? So I'm going to change little parts of my protein and see how that affects its ability to break methane. And by doing this type of experiment, I can ask very interesting questions like, why do we need the penny, like the copper, and what does it do? Where does the methane bind so we can trap it, right? And the most important question, where is the hammer in the protein that breaks the methane? And so if we figure all this out in the magical future, the perfect future, what we can do is, with this knowledge, take the bacteria and the methane, engineer the bacteria so that it can poop out our gasoline. That'd be great. Or if that's just too hard, then what we can do is make actual technology that mimics how pMMO and the bacteria works. And again, make gasoline. Wow, that sounds great, right? And hence, I've just shown you a story of my belief that nature is always smarter than us and has the solutions to most of our problems. We just have to look hard enough because nature has billions of years before us. And I believe that's why it's really important to still study biology. And here's a picture of, the human footprint on physical Earth. And look at this tiny little bacteria that can do something none of us can do. And hence my motto, don't fight nature, embrace it, and especially copy it. Thank you.